Welcome! This is the third tutorial of a three-part series on how to get started with the gas turbine performance software, GasTurb. The tutorial series provides an introduction to GasTurb's user interface and its most frequently used features. A basic understanding of gas turbine performance calculations is recommended to make best use of the software and follow the tutorials. In this tutorial, we will learn how to perform off-design simulations in GasTurb. We will start with calculating a single off-design point of a turbojet engine. Then we will examine how GasTurb uses component maps to calculate the off-design behavior. We will calculate the engine operating line and, in addition, simulate a handling bleed that improves the compressor part load behavior. For this tutorial, we will use a simple turbojet engine. We select the turbojet from the Jet Engines tab and choose the configuration without afterburner. We keep the pre-selected performance scope and click on Off Design to open the Off Design Point input window. GasTurb automatically loads standard maps for each compressor and turbine in the background. We can select other maps or change the map scaling points by clicking on Maps in the Off Design Point input window. The Component Maps tutorial provides an in-depth introduction to using maps in GasTurb. First, let us have a look at the calculation results before modifying any of the loaded data. For that, select the task Off Design Point and run the Off Design Point calculation. The results of the Off Design Point calculation are displayed. As we did not change any input data, the calculated Off Design Point is equal to the design point, and therefore the contents of the Summary tab are identical to the ones of the design point. Let us have a look at the compressor map. The compressor map shows the compressor efficiency and relative spool speed as a function of the mass flow and pressure ratio. The cycle design point is marked with a circle, whilst the yellow square marks the calculated off-design operating point. As we calculated the design point as an off-design point in this special case, they are identical. Whilst opening the off-design input data window, GasTurb already calculated the cycle design point of the turbojet. The standard compressor and turbine maps faded in were then scaled accordingly such that the scaled reference point of the component maps matches the calculated design point. In this case, the map is scaled so that the scaled reference point is in line with the design point with a pressure ratio of 12, a design compressor efficiency of 85%, and a reduced mass flow of 32 kg per second. Now we will have a look at the turbine map. The map shows the turbine efficiency and relative spool speed as a function of the turbine pressure ratio and the product of corrected flow and corrected speed. The presentation of the design point and the off-design point is the same as in the compressor map. With turbine map or maps, we can switch the display to a different map format. The axis assignment of the turbine map can be selected. Either the pressure ratio or the corrected work can be selected for the y-axis. The x-axis may be displayed as either the product of corrected flow and corrected speed or corrected flow. In this case, the turbine pressure ratio is shown versus the product of corrected flow and corrected speed. When choosing the corrected speed as x-axis value, the corrected flow is shown as contour lines in the percentage of the maximum corrected flow in the map. When choosing the corrected mass flow as the x-axis value, as is standard for the compressor, the readability of the map can be poor if the speed lines collapse in the region of choked flow. We click on the Stations page to get the details at the thermodynamic stations. Note that the engine geometry is fixed during the design point calculation. In off-design simulations, the static pressures and temperatures are calculated using the flow areas calculated at the design point. Let's close the output window. Now we will examine an off-design point and vary the burner exit temperature. We can choose whether the relative spool speed or the burner exit temperature is given. We switch to the burner exit temperature option and reduce the burner exit temperature to 1200 Kelvin for our next off-design calculation. The predetermined burner exit temperature is given in the result window. Compared to the design point, the engine mass flow and the pressure ratio are significantly reduced, leading to a lower net thrust. In the compressor map, we can see the off-design point with the reduced pressure ratio and mass flow derived for a burner exit temperature of 1200 Kelvin. Iterations are needed to simulate the off-design behavior of a gas turbine. To see which iterations GasTurb uses for the off-design point calculation, return to the Input window and select Iteration Variables. There are 4 iteration variables for the turbojet engine. Beta values are auxiliary coordinates used for compressor and turbine maps, as shown in the diagram. The beta values don't necessarily have a physical meaning. The beta coordinates are used to avoid convergence problems in regions of low and high corrected speeds where the pressure ratio and mass flow relationship often becomes ambiguous. The beta values are defined between 0 and 1. Therefore, beta values out of this range hint at possibly invalid results. Depending on the chosen calculation mode, either the spool speed or the burner exit temperature is predetermined, whilst the other is calculated via iterations. With T4 fixed, the spool speed is another iteration variable. Finally, the temperature deviation of the recirculating bleed only needs to be iterated if a recirculating bleed is considered. As we did not employ such a bleed, we do not need to consider this, and it will stay at 0. Starting values are defined for each iteration variable of the iteration process. They are taken from the last case calculated or when a case fails to converge from the last guess. If an off-design calculation fails to converge, the values may indicate where the problem lies and can be manually adjusted. These are the iteration variables for a simple turbojet engine. For more complex gas turbine configurations, additional iteration variables are used. Further information regarding the off-design iterations of GasTurb can be found in the GasTurb manual. Now let us calculate an operating line for this turbojet engine. We select the task Operating Line. We go to the Basic Data branch, set the HPC spool speed as given parameter, and set it to 1. Now, run the operating line simulation. The operating line commences with the point we just defined in the Input Data window. Then a series of points with decreasing gas generator spool speed will be calculated. The number of calculated points and the step size can be specified. We choose 20 calculated points and a step size of 2.5%. Now, let us start the calculation. GasTurb offers the possibility to calculate several operating lines with different input parameters. For our first calculation, we will stick to only one operating line. We open the compressor map. The operating line of the compressor is displayed as defined before with 20 points and a step size of 2.5% of the relative spool speed. At low part load, it becomes obvious that the compressor is in danger of surging. In order to cure that problem, we will employ a handling bleed. For that, we return to the Input Data window. We click on Controls and select Bleed. The Handling Bleed Schedule window opens. Using a bleed, a portion of the compressed air is blown off in order to lower the operating line of the compressor. We define that the handling bleed is closed above a relative spool speed of 0.8 and fully open below a relative spool speed of 0.6. Below this value, the maximum relative amount of bleed air will be taken from the engine mass flow. We define this value as 0.3, that is, 30% of the compressor mass flow. As displayed in the graph above, the proportion of the bleed air extracted increases linearly in between the defined spool speeds. Now we close the window. We will later on activate the bleed manually. Therefore, choose No for the automatic bleed activation. We rerun the operating line simulation. This time, we choose to draw more operating lines. The input data for the different operating lines is shown. They correspond to the possible configurations in the data tree of the input data window. We activate the automatic bleed for the operating line number 2 via entering a 1. We adapt the title of the new operating line and run the simulation. The two operating lines with and without bleed are now displayed in the compressor map. It is apparent that by using a bleed, the part load behavior of the turbojet could be improved. Let us try to get further information on the impact of the handling bleed on the engine performance. We draw the picture with the access assignment, specific fuel consumption over net thrust. As we can see, using a bleed in part load operation considerably increases fuel consumption. The bleed mass flow is not supplied to the combustion chamber, does not contribute to the thrust, and its compression energy is lost. Achieving the same net thrust with bleed thus requires more fuel to be injected in the combustion chamber. Now let us have a look at the burner exit temperature when using a handling bleed by choosing the burner exit temperature T4 versus the relative corrected spool speed. The burner exit temperature increases significantly in part load when the bleed opens. This is due to an increasing fuel-air ratio. Once maximum handling bleed is reached, T4 again drops with speed, as it would without a handling bleed. This concludes the Introduction to Off-Design Simulations tutorial and our 3-part series on getting started with gas turb. There are many further tutorials covering a wide range of gas turb's tools and functionality. Pick any tutorial that you are interested in. We hope you have a great experience using gas turb. In case of questions, don't hesitate to contact us.